Okay, so hello everyone and good morning. This is the fourth webinar in our DYNAmore Express webinar series, which covers different topics throughout the LS-DYNA and the DYNAmore portfolio. Today it's going to be on me to present recent mapping capabilities and recent developments to our rather new mapping tool, Envyo. When I looked through the list of participants, I figured that some of you have already attended some of the presentations I've given in the recent years. So some of the slides might be familiar to you, but we've also been doing new things. Especially my colleague Tolga Usta, who is also listening. He implemented quite some nice new features in the recent past, and I'm going to show those to you. So we can't see each other right now. Just decided to have a small slide with a picture of me. So on the right, this is me. At the bottom, this is the DYNAmore office, which is not completely empty right now, but we still got a couple of people working there. Nevertheless, just a few words to my background. So I studied aerospace engineering at the University of Stuttgart, and since 2011, the DYNAmore GmbH based in Stuttgart in Germany at this headquarter, which you see at the bottom right. I started there working as a project engineer, mainly for projects and support for everything which is related to composite modeling in LS-DYNA. So short fiber reinforced composites, continuous fiber reinforced composites. Over the years, I took over giving the composite courses from my colleague Stefan Hartmann, who's right now with LSTC, doing isogeometric element formulations. So for now, it's basically on me and my colleague. So just an announcement, we will have one of the composites classes being taught online on May 18th to May 20th. So everyone who's interested can join these courses. And yeah, since a couple of I'm doing Envyo development. So we started the development of Envyo a while ago, and we've already have deployed it to some customers. People use it for different applications. So what you're going to see today is a large variety of different applications, different enhancements which we made, but also some new things, which I will talk about briefly. So this brings me to the end. Just give some summary slides on what the basic idea of Envyo is. What is our motivation to write a mapping tool? Because there's other mapping tools around as well. We have some advantages, but also restrictions, and I'm trying to cover those briefly in these motivation slides. Then we will have a look at the application examples, and that's where we're going to see some new things. We've actually been figured that we want to make the tool a bit more usable for customers, so we're started to set up very simple examples, very small LS-DYNA models, which shall provide information about the capabilities we have with the tool. And I will introduce some of the examples, these small examples. I will introduce some of them in this presentation, and we will add them to the package which we provide to customers when we share Envyo with others. So that same as you have the DYNA examples, there's going to be Envyo examples, basically, which demonstrates the capabilities, and I will talk about those. I do have some bigger examples as well, which are just, have been presented in the last years. I will just go quickly through those, but so that you see there's also bigger examples being possible to which Envyo can be used for. And then I do have a quick comment on future plans and summary. Since this is quite a large group, when I received the list of participants, we had like 50 participants registered. I'm not sure if everybody signed in. So we will skip the questions and answers, but there's going to be an email provided on the last slide. So if any question comes up, please do not hesitate to contact me with an email just right after the course or in the upcoming days. So I'm going to start with the motivation. I think some of you who've attended these presentations, they know this slide already. What's the idea of Envyo? On the left side, we have a source mesh, which is basically coming from any software which you could think of, or actually we try to cover all different kinds of data on the source side. This can be images, image data, for example. We will see that later on. The simplest way, of course, it would be that on the source side, you have a LS-DYNA mesh, which come from a process simulation of any kind. So a draping simulation, for example, or a metal forming simulation. On that source side, you have a material model, for example, can be isotropic, orthotropic, anisotropic, whatever you can think of. In DYNA, those who are familiar with it, we have history variables, stresses and strains as an output. And the idea is to collect all these kind of information which we have on the source side, which is not restricted to simulation only, but also to experimental data or even pictures, as we will see later on in one of the examples. And on the target side, and this is where it comes to one of the restrictions, we have an LS-DYNA mesh. So the intention of Envyo is basically to take everything or every information which we can get from other solvers, from other softwares, from experimental data, from measurements, and to put them into an LS-DYNA analysis and to make them accessible via the DYNA in file, which is basically the main include, which you would also get, for example, when you run analysis using the interface Springback LS-DYNA keyword. And this is a file which contains all the information necessary for further information. So it contains the history variables, the stresses, thicknesses, strains, and so forth. What we do with Envyo when we have data and we have a target mesh, we take these data, sometimes geometry matching, simulation data, but also measurements might be aligned or provided in different systems. So we do a geometry matching in the beginning. Then we do point cloud-based mapping. So we're looking into where are the specific data stored. So thicknesses usually are provided on the nodes. If you think of element shell thickness, you have 4 values for the nodal thickness for each of the nodes. We do have orientations which can be provided for the element as well. If you think of element shell beta, for example, or element solid ortho. But these directions can also be provided on integration points. So you can transfer these orientations onto element shell composite, for example, and then you have a whole set of integration points through the thickness, which hold information for the orientation. And we do data transfer. Depending on the process we are looking on, we have to do a homogenization counts, for example, for short fiber reinforced composites. Also for other processes, I will have a small example for a Bake-Hardening process where we actually take temperature result data, which is stored on nodes, and map them onto integration points and assign specific values for a specific material based on the temperature and the resulting hardening degree based on this temperature. So we do a homogenization. Sometimes we have to do history variable handling. So we have to move history variables to specific positions to make them accessible for a specific material model. And then we write a DYNA-in file, and then you should be good to go to run a further LS-DYNA analysis with a new DYNA-in file containing the data which you want to consider. Just a brief word on geometry matching. For now, we consider two algorithms. One of them is more experimental but fully automatic, which is the 4-point Congruent Sets algorithm. The other one we use is the iterative closest point, where the user provides us a set of nodes which should be matching. This is the algorithm most commonly used. I think you will see it later on in one of the example input files. For mesh operations, we can do scaling, rotations, and transformations. We've also started to make it possible that you can do multiple of these transformations. And of course, you often need to do a unit system conversion if you do have one simulation being run in one consistent unit system, but the crash simulation is using another unit system. You have to make sure that the parameters are transformed properly, the lengths are scaled, the stresses are scaled, and this is what we can do internally with it. The mapping is based on point clouds. We have a bucket sort algorithm implemented. You see a very coarse bucket sort in which I plotted here on the right, where you more or less see the buckets which are generated. Actually, we do that much finer, but for presentation purposes, I have it provided here this way. As I said already in the introductory slide, we do have element-based data, we do have integration point-based data, and node-based data. We do create a and transfer the resulting data. The data most commonly is used based on a closest point search, so we're just looking for the nearest neighbor, take the data and transfer it. Nevertheless, we've started investigation on scalar value, averaging, and interpolation. So we can also use an inverse distance weighted averaging, which is also called the Shepard's method. We've also started investigations for tensor real data averaging and interpolation. This is a bit more complicated and was part of Tolga Usta's master thesis last year, I think. And he's been looking into the effect you get when you consider the directions of the tensor or the invariance of the tensor and how these might influence your simulation's results. So this is a bit more of an, let's say, advanced setting. Nevertheless, we try to make those available to users too, and I think it's especially for short fibers, it can be an interesting field to improve the accuracy of the mapping, at least to some degree, when one of the tensor interpolation methods is used. The problem with tensor information, with tensor data interpolation, is that you usually use one of the information, either the direction or the shape of the tensor. So you have to find a compromise between what would be good. Nevertheless, most people stick to the closest point data transfer, and I think one of my sayings always is at least consider some of the information you already have from experiments or from other experimental data and start with that and see if you can get an improvement, and then you can focus on the details and see if we can get more and better results when we do scalar interpolation or even averaging of the real data. With that, I'm going to continue with the application examples. This is an overview slide which shows a large variety of the mapping capabilities which we already have in Envyo, so you could map from beam elements to shell elements, for example, if you do have a mesoscopic modeling. A standard application is mapping from shell to shell meshes. We're working on shell to solid mapping. I think this is also realized. Quite commonly used is mapping from mold flow to shell or from mold flow to solid. We also allow the user to provide an arbitrary point cloud, for example, in a comma-separated file, which contains data, and he can map those onto mesh as well. We do have a support for HDF5 since quite a while. I will comment on that later on when we come to the respective examples. And there are actually even more applications one can think of. If you have any idea in mind, you have any mapping application which you need for your DYNAmesh, please come up with the ideas. We are always looking for applications and further examples and further enhancements for the tool. I'm going to start with a very new feature we've just been implementing like in the last 3 weeks, actually. And it's a mapping of Plybook-Data. So recently we learned that some preprocessors, I think ANSA is one of them, or CATIA, they are able to provide Plybook-Data and they can output them in DYNAmeshes. So you have an analytical draping simulation, so to speak. And what they can do, they can write a mesh which contains LS-DYNA elements. And these meshes, they hold the different plies, as you see here on the right side. I think these are 5 layers over the thickness. And each of these layers, they contain the fiber directions as element shell beta. If you want to move over to a structural analysis, you want to use that layered structure. You just want to have a single layered shape. And if you want to use that, you want to make these as a staggered shell containing element shell beta. You want to use those with element shell composite or even element shell offset composite. Briefly on the next slide what the offset means. What's, let's say, special about the example and what explains some of the features which we have is that one of the layers is overlapping. So for example, if you have a cylindrical part, and you can imagine that if you do a hand laminating process and you put one of the layers on top of the other, or you wind it around that cylindrical component, there will be an overlap of the layers. And this is what we see here in the middle of layer 2, that one of the layers seems to be going on top of the other, but they have the same part ID provided in that element shell beta mesh. What we have here on the right is layer 5, which is the top layer, where you can see, for example, that there's a gap which is opening here. And this gap should, of course, be considered on your target. The target mesh here is just a flat plate, basically, same as the base layer. So in some areas, you will have multiple layers, which are introduced from layer 5. In some areas, you have less layers because there's something missing here due to that opening of layer 5. And this is basically what we see here on the next slide when we've done the mapping. So there is this is a fringe plot of the composite ply thickness after the mapping process. You see already we've had 5 initial plies, one of them overlapping. We've introduced them with an initial thickness and get a resultant thickness for the total composite ply, basically, as it's fringed here. We will have different thicknesses in certain area depending on the structure we have. Now the input is as follows. So you basically provide a source file. The source file contains the element shell beta. You have a target mesh with the targets file, and you provide a file name for your mapping result. Then you have the orientation file. Orientation file basically, for some instances, for example, mold flow, they are provided in a different file format. That's why we say, okay, it's an orientation file. If you use beta here, Envyo knows that the element orientation or the material orientation is provided as element beta, and it will look for that in the input file. Then you can define the stacking sequence, basically in whichever way you want. So you provide the source part IDs. So you provide the part IDs of the source. You provide the material IDs, material ID, which you want to see being used on that integration point. So you could actually say, okay, I'm going to have, if I have a glass fiber, carbon fiber, composite with some inlay, you could provide different material IDs here for the integration points. And you can define the thickness of the plies here. And you provide the target part ID. And then there's a flag which allows you to consider these overlapping layers. By default, we don't consider those. So you won't have of this second layer into two plies as we see it here. But if you turn on this overlapping coefficient, we will also consider and look for elements which will overlap in specific areas and consider that in the stacking sequence of the resulting element shell composite card. So what you get by default is you get element shell composite. As you see it, yeah, basically here you get fringe. You can also do a thickness plot in LS pre-post. The default is that the shell plane, which is provided, interpreted as the mid layer of your composite. In pre-post and now as well in Envyo, if we do the mapping, we do have an offset option where we can say, okay, it's going to be the upper surface or the lower surface. So we can automatically adjust to, yeah, let's say to the upper or the lower surface to consider the direction of the stacking sequence in the composite part. And that's basically what we see here. So you can either move, it's always referring to the element normal. So if you use the offset option flat upper, you're going to say, okay, the shell representation is the upper surface of my component. So the layers, in this case, below that top surface. If you use the flat lower flag, it's going to provide it on the top, this shell surface. And another parameter here, which you can use for the Plybook shell mapping, is a projection tolerance, which allows you basically to manually define a scale. What we see here is the mapping of that fifth layer, the one which is opening up. The green arrows are the ones which are the mapped orientations, and depending on how you choose the tolerance, you're going to have a different number of elements being assigned a ply and a respective orientation and thickness. Another new feature, or well, it's not so new anymore, but what we have is multiple transformations, which allows you to allows the user to define multiple transformations if the components are not matching very well. I created a very generic example, basically, which I call the sawtooth example, because I took this example and cut it some specific areas here, and I assigned numbers of effective strain of 1, 2, 3, 4, and 5 from left to right. So this here is source mesh, and at the bottom I have the target mesh. And if I just one transformation, what I will get is, okay, this main area seems to fit more or less to the target area, but these teeth here, they don't match. So if I do the mapping with just one transformation, what I will get is I will just, here I get at some point I get a value of 1, but then I get different values at the different positions, which do not correspond to the tools I see. And you have that, for example, if when during your design process you're going to change the design of your component, you do have holes in different areas, but you just have one forming simulation of that early stage. But to some degree, you want to consider these results and map them. Then it might be necessary to perform multiple transformations and to make sure that you get the values transferred properly to each of these teeth, so to speak. And what you can do is you can define additional transformations. For this case, I use 5 additional transformations I have an initial transformation for the main body of that component, and then I do have 5 additional transformations for each of these teeth, so to speak. And the input is quite simple. You're going to define how many additional transformations you want to have. And then same as for the general iterative closest point algorithm, you provide nodal pairs on the source and on the target side, which should match to each other. So this is basically what we have here. Depending on how many additional transformations you want to have, this can be quite a long list. And you provide an element set file which contains the elements which should be mapped step by step with these additional transformations. What we see here on the right is the initial transformation, and then you see that for the additional transformations that each of these tooth, they now fit to the corresponding partner, so that finally we get the values properly transferred onto that target mesh as well. With that, I'm going to continue with the GUI development we started, because I think it fits here quite well. Actually, it can be quite strenuous to define all these points and parts if you don't have a preprocessor. So we actually started to work on a GUI here. It's not available for all the applications we have, but it's, for example, available for shell-to-shell map. What it basically should do, it should help the user to show all the options which we have in the mapping, depending on which map case you select. And then to easily set up, select the files which you need, to turn on the transformation options, to select the mapping algorithm, to select shell options for the output, for example, to provide further information on what you want to map, if there's a specific handling for the history variables and so forth. And then what it basically does is just outputs the mapping info file, which we've just seen in one of the slides before, which can then be used for the mapping, or it can even be run straight out of the GUI. So you just click and it's going to start the process of the mapping. We picked the GUI development in this case is because if you want to, for example, use a transformation with the iterative closest point matching algorithm, you have to define the nodal pairs here, and this can be quite strenuous if you have to figure them out in your preprocessor on one side, and then you have to copy paste them into there. Also linked LS free post to the GUI, so you can If you start it initially, it's going to tell you, okay, there's no config file, so the program does not know which preprocessor you're using, so you have to select the installation path of LS Prepost. What it then does, it basically opens LS Prepost, the identifier option in LS Prepost, and the target size. Then in the Envyo pop-up, you can select accept nodes, and it's going to insert the nodes directly into the Envyo application, and is then used for the mapping. So I think this is quite a useful feature and will be extended probably quite soon. But this should already be working if you have multiple transformations, for example, and you have to select different nodal pairs. It automatically loads your model source, and then based on the information you provided beforehand, and then you can just select the nodes in Prepost, and with accept nodes, we will figure out which nodes you've selected and put them on the source and the target site. Yeah, and as I said, what it basically does, it writes the mapping info file with the provided information, the additional nodal pairs whatsoever, and then you click on finish and run the mapping. I've also started to working mapping evaluation. For now, we just do that for shell mapping. And what you basically get as a user, if you turn on mapping evaluation, which is called evaluate mapping equals to yes, we're gonna create a new instance, a new file with the ending .comp, basically for comparison. And what you get, or what you can post-process from there, is as the last history variable on the target mesh. The first thing you get is for all the history variables and stresses and thicknesses, whatever you have, you get the difference between a standard closest point and another algorithm. Then as the following history variables, you first get the distance between the integration points where the data has been transferred. And what you also get is you get the angle between the normals of the shell elements from source and target site where the data has been transferred. This can be an interesting feature to evaluate the mapping to some degree. Started to have further options for an equation solver and also for table lookup. For now, it just works to initialize additional history variables, which can provide it in a specific format. So here, for example, you have initial parameter x. Then you have, in the standard LS-DYNA input file format, you have provided element IDs. And with these element IDs, you have history variables. I just picked random values between 150 and 300, just because to have a demonstrator case. And you can consider those data with additional element history variable file. And in this case, this file would be results of parameter 1, whatever. You can have multiple of these files. And you can also have a lookup table. In this case, data parameter 1 epsilon, for example, effective plastic strain, is this table, which contains 3 columns. And basically, it can contain columns, but here you can basically select which columns you want to consider. So we're going to consider column 1, column 2, and column 3. So this is just for reading the we have for solid and cell initialization here, which is the initialization of, and the next one is the reading of lookup tables. And what we can see with them is what we can do with them is basically what we see on the next slide. As I said, I selected random numbers between 150 and 300, and here I selected random numbers between 0 and 100. So you just get scatter plots. It does not have to say anything. It just says that it does something. We do have variables now, which we can use already. Processing with the equation solver. So additional element history variable is one of these variables which we can use in the equation solver. History variable is a variable which we can use for the equation solver. Then I've said, okay, it might be useful maybe to use the element length. So if you use that parameter, we're gonna, when we process the results on the elements, we're gonna derive the element length from the element we're looking at right now and use it for the transformation, and the effective plastic strength. But this can be extended, of course, to further values. What we do here and what you see in this red box on the left is basically that I take the results from the additional element history file 1, which is additional element history 1, and I write those to history variable 2, and I get this as an output here. History variable 3 is basically the same, just with the other file. And history variable 4, I performed a mathematical operation. I calculated the absolute value of history variable 3 minus history variable 2 times some arbitrary other value, and it gives me some result on history variable 4. So the result of this is an equation parser available, and we can also use these lookup tables. So if you have a look provided, there are basically two options what you can use with the lookup table. You can do a linear interpolation between the values which I find in the lookup, and you can also do a next neighbor selection. Basically, you select the value which is closest to the one which you're referring to, and you can use those lookup tables to assign them to specific values, for example, to the effective plastic strain or to a history variable. So here, for example, we take lookup table 1, we do a linear interpolation, and the values we use for the interpolation and to go into the lookup table, in this case, is history variable 4 for column 1, the element length for column 2, and the result will be column 3, which are the ones which I provided first when I was reading in the lookup table. For history variable 6, I'm using lookup table 2. I'm doing a next neighbor comparison. For the comparison of the first value, I take the effective plastic strain, which I just calculated beforehand, take the element length for looking up in the second row, and then I look into the next column 3, which will be results. And this is basically what you see here, is the fringe plot of this effective plastic strain or the history variable 6. Again, this is very values, and they don't have a meaning. It was just to showcase, to show the abilities which we have. Here, for example, what you see is you see a fringe plot on history variable 8. I assigned the element length to, which is reasonable. I do have quite common similar element lengths here. The element lengths are changing here in the bottom area, so I thought this is another nice picture to the random numbers. Here you have something which is more realistic. And another flag I want to introduce is the maximum number of history variables. So you can, for example, use a higher history variable to store intermediate values during your calculations if you have complicated equations, for example. But then you just, here, for example, I just stored history variable 6 on history variable 9, but I just output 8 history variables, which I will then need for my calculation. So it's a nice thing which you could use there. We've been talking about in the past quite often about the process chain for short fiber reinforced plastics. We've also projects here together with Opal in the past. There are quite a few papers around which you can look for and see the work which we've done there. But pick up another example, which is the Moldex 3D to solid mapping, and I got it provided from my by DYNAmore Nordic, who've been testing these features. It's a very simple example. Basically, they have a plate here, which is a result output of a Moldex file. It's quite a messy mesh with yeah, a lot of part IDs. Anyways, we can use it to map fiber orientations and calculate the stiffness tensor, for example, for MAT 157, but also for MAT 215, which is MAT for a micromech. As an alternative, you could create element solid orthos. For Moldex, we do have also the consideration of weld lines. So if a weld line file is provided, which provides information regarding IDs which are within the weld line, the user can define a weld line part ID and also a weld line search radius. So elements within this user-defined radius are also assigned to this part ID. And it can be, for example, given a different part ID and also a different material ID, have weaker in this weld line area, as an example. If you want to target, for example, MAT 157, you use the EHIS flag equal to 1. And I picked this example to show some LS pre-post features, which I come across quite often, also by other customers. Took the chance to make some slides here and show some differences which we have also when we initialize on solid elements. So if you use the solid ortho option, there are two vectors which you have to provide. One is the vector A and one is the vector D. The vector A is the main material direction provided in the global coordinate system, and the vector D is a vector which lies in the same plane as the main direction of the material and the second material direction. Also provided in a global coordinate system. Whereas if we initialize the orientations, for example, for MAT 1 in initial stress solid, we often refer to the Q values. For MAT 157, we use Q11 to Q13, which is the first vector of the material direction, which is now provided with respect to the element coordinate system. And the other vector which is used for initialization is the vector Q31 to Q33, which is actually the third material direction. And what we see here in this very simple example is we have the global element coordinate, the global coordinate system, and then I plotted the element coordinate system. And if I look at the results of element solid ortho, I see, okay, my main A1, A2, A3, the main direction is pointing into global direction. As if I look into initial stress solids and I look at the respective Q value, I will figure out, okay, this is now an elemental coordinate system. I figure out the highest value in the main material direction is given on the third tissue variable. So it's going to pointing in element Z direction, and the element Z direction, in this case, as you see, X is pointing in global Z, Y element is global and pointing in global X. So the Z direction of the element is pointing in global Y. So we will have the same result if we initialize with element solid ortho or with initial stress solid. But the data is outputted differently in different coordinate systems. And that has to be understood and therefore might be quite cumbersome. And therefore people actually asked, how can we How can we see these directions? I've done a mapping, I get an initial stress solid card, and I can't understand if the results are right or wrong. With a small trick. The first thing you have to do is you have information on a quite commonly known DYNA support website, where we have, for most of the material models, if they are not listed in the manual, for most of the material models, we have the orientation information and other history level information. They are written to this file. So you have to look up to look up the information you want to post process here, and then if you have to make sure that if you run your analysis, you have to turn on database extend binary. The maximum number of integration points should be correct. And of course, you have to request the specific amount of history variables which you want to post process. If you just want to see a quick analysis and see, okay, did I get my direction right? You can just stop the analysis after one cycle. So in control termination, there's this end cycle flag equal to 1. So you just run one cycle, and then you load the D3 plot into Alice pre-post. And then we have a new feature, which is also implemented by our colleagues from the Nordics. You can go to post and then to vector. And in vector, there's a drop-down menu where you can basically get all different vectors, such as the normals, or you can get velocity vectors or the main stress vectors. But there's also a value which is called history variable curve. And then you have history variable x, history variable y, and history variable z. And if you define positive values here, the values you define here, they are history variable positions. And if you define positive values there, they are interpreted in the global coordinate system. This might be the case for entries for material 249, for example. If you use that for draping analysis and you identify your orientation positions, you provide positive values here to get a plot of the orientations which you have. If you know that the elements or the orientation is defined in the element coordinate system, you provide negative values here. So I did this in this case for MET 157. So it's -4, -5, and -6 for the main orientation. And for the outer layer, we get more or less aligned orientations with the flow, whereas for the middle layer, it's a bit more random, which is something which you usually observe when you're looking into such kind of materials. We also set up a small example for draping analysis. In this case, 139. You can output the fiber orientations in this material model with the post V flag, the specific flag which we have, which allows us to get certain information such as the fiber angles, the fiber IDs, fiber straining, fiber direction, and so forth. And we've implemented a mapping capability. If you output all these information, so you have to set post V equal to 63, we will need at least 31 additional history variables in the DYNA-in file, and then we are able to map these results of a draping simulation onto a structural mesh. So to create this plot here, I used history variable 13 to 22 in global coordinate system with the same plotting feature which I've just shown on the slide below. Another remark which I want to make here, for any kind of simulation where you want a DYNA-in file for a further mapping process, you can use the control card interface springback LS-DYNA, where you define a part set ID which contains the part which you want to use for the further processing, and the number of variables which you want in the output for the mapping. And then you automatically, after each analysis, get a DYNA-in file which can be used for a further mapping process. So yeah, this is what we've done here. What we do when MAT 249, those who've worked with the material model, they figured that you can have or multiple fiber directions within one integration point. Case for the standard LS-DYNA crash material models. So what we do is we split into 2 plies holding the different so here we say, okay, how many fibers do we have for each integration point? These are provided for them. Then the source material model has to be defined. The post V flag, for now we just support 63, but we can imagine to enhance for other post V flags as well. Then you define the number of in-plane integration points you want to have, the number of through thickness integration points. You can map stresses and thicknesses. And this is the mapping result. I mapped these orientations from the source side to the target size, and I used for visualization, I used element tool, element edit, and here we have in pre-post, we have a composite tool, which allows us to select a part ID, which is holding the element shell composite information, and then we can click through the different plies, select the directions, or fringe plot the thicknesses. All the things we've seen in the slides before can be done with this composite tool in LS pre-post. I'll go quickly over that. So there's other people using this feature already. I've for Asia in the past who used the mapping for their MAP 49 transfer to elemental composites. We've also had a PhD thesis running at BMW. They did draping analysis as well, but they mapped them onto solid meshes. So I created element solid ortho, but I used another version of MAT 249 with single fibers, and they improved analysis for certain components for composite parts here. We've also seen those slides quite often. We can consider meso models by mapping beam elements or even shell elements onto structural meshes. So if you have a mesoscopic draping or braiding simulation, or even a open reed weaving process, we're doing these works together with the DLR within the ARENA 2036 at the campus of the University of Stuttgart. Transfer these data to shell meshes and to consider orientations there as well. There are different methods. One is the closest point method, so we just look for its neighbor, but there's also a search radius option, which allows you to look into a specific search radius, and if you don't find anything in a specific radius, you're going to assign another material which can hold matrix properties, for example. You can also consider the undulations. So you do have varying orientations over the different layers. I can also consider, this is quite sophisticated, for mesoscopic shell mesh, I can also try to calculate the thickness offset between the fibers which are transferred onto the shell mesh. So also the thickness distribution can also be considered in this mapping approach. We've also started to work on mapping of representative volume areas. Elements, what I need for that is basically a set of material properties for dedicated representative volumes. And then I go through the source mesh, looking for representative volume elements, figuring out which representative volume element is represented in a specific area, and then assign respective material IDs to that area on the target site. Another new feature which has been enhanced, I've shown that already at the last European LS-DYNA conference, but it's basically 2D to 3D shell mapping. what you basically have is you have a 2D shell element, 2D shell mesh, which you performed an analysis with. And then you can basically have a target mesh, which is the full body of shell elements. And I do automatically the rotation of the 2D mesh in Envyo. And I can also, in this example, it's a bit boring because the thicknesses are equally distributed. But I can also calculate the thicknesses in the respective areas and transfer the thickness onto the target mesh. And I can also transfer, sometimes you have element masses, for example, here. These can also be considered in this mapping process. The difference in this case is to initial lag mapping. There's a keyword in LS-DYNA called initial lag mapping. This automatically creates you the target mesh, whereas in this case, the target mesh has to be provided, and Envyo does the rotation and the transfer of the data. And here you just see an output. Here we have 4 layers of and target mesh, and we see in the respective areas and the respective integration points that we do have higher or lower von Mises stresses in the respective sites. So integration point 1 would be the inner layer here. So we see that here in the corners we do have higher stresses, whereas here in the outer integration point 4, which is this layer, we do have higher stresses in the middle of the component. Another new feature, which is actually being tested right now, is the consideration of the process. So if you have vehicles, they usually after the manufacturing, they get painted, as far as I understand, and then they go into a, let's say, drying oven, and the vehicle goes through that oven, and you have the oven applies temperatures and in different areas, and you get different temperatures in different points of the vehicle. And especially for aluminum structures, this has an effect on the resulting strength, on the yield behavior, and therefore people want to consider in their crash analysis. So the first thing we had to do is we had to make these Theseus is one of the softwares which is available for such simulations. We had to make these Theseus data available for Envyo. So they usually come in the provided HDF5 format, and for now we can read those, and we use the JMAC equation with provided parameters N, T, and Q, which can be determined by experiments, and then are used as an input for Envyo. We can calculate the local hardening degree, and from that can assign with material 251 mapped to tailored properties. We can assign different hardening degree to local areas, and then refer to different tables and different curves, which consider different plastic behavior for these different hardening degrees. The extension I've done here, compared to the presentation I gave last year in Koblenz, was that I'm now also considering LS-DYNA's LS-DA format as an input to calculate this hardening degree, but also CSV formats contain comma-separated time and temperature values, and given a specific temperature over time, you get the development of the hardening degree as an example, and we can do that now for full vehicles as well, and therefore get local varying properties. Another feature also presented last year is image processing. So what I can do is, if you have an image which can be easily transferred into a grayscale representation. I did that here with GIMP, which is GNU Image Manipulation Program. You get a grayscale value representation of your image. Basically, each value here, you have the number of pixels. It's like 803 pixels in this in X direction and 832 in Y direction, and then you get for each pixel, you get the grayscale value. And you use that to assign different part IDs to your target mesh. In this, I used 2 part IDs. So the part IDs which have grayscale value between 0 and 195 get part ID 3. If the grayscale value is 196 and 255, they get part ID 4. So what's the application for that? The application for this was wood forming, actually. So for quite expensive parts with nice interiors, they do have these sheets of wood called veneer sheets, I think, for which they do a forming process. And usually the worker, by looking into the wood sheet or looking at the wood sheet, he knows, okay, this one's formable. This one won't break during that process, but if he looks at another one, he says, okay, this one won't hold the forming process. So the idea behind this was to actually, because these pictures are taken from all the veneer plates which are being processed, basically. These pictures are taken, and the idea is to consider the results of these pictures in the analysis. So we came up with the idea to transfer them into grayscale and to define an arbitrary number of different parts, basically. The different effects of the early wood and the late wood in this material. I'm actually not an expert on wood processing, but that was the idea. And here I just did a small case study on the effects. It's the same picture where I basically had a different grayscale range values assigned to different part IDs and ran a small Nakajima simulation. And of course, you see different stress distributions in the different areas because they do have different stiffnesses assigned to the different regions of early wood and late wood. I think you can also use these for other applications. Wood was the first application or the first idea where we tried to use this pixel mapping, but I could imagine it for other applications as well. Another feature is point cloud to shell mapping, where we have a finite point set analysis method, which is creating points which hit a plate and therefore create a pressure. Do with it, we create load segment shell cards, and these load segment shell cards can then be used on a non-rigid elastic plate to apply different deformations to that plate. We've also tried to do the mapping for a huge vehicle. It took a while, but it worked. So people are trying to use that and see if they have another way to couple through another software to couple fluid analysis to some degree with structural analysis. Within the arena, we have a feature for initialization of material properties. We do that for MAT 157 as well. So the user can define a range of material properties for matrix and fibers. And then we do an arbitrary distribution of these properties. And then you can, for example, run RVE analysis for virtual testing cases. So this was the intention of this keyword. We are collaborating with the VMAP community. VMAP is a project where we're looking into standardization of simulation result data. So the idea is to define a software vendor neutral data format so that between the different softwares we can exchange simulation result data. And for example, if you use Abacus for your process simulation and then do structural with LS-DYNA, you can simply use the VMAP file format, which is then readable and understandable. Yeah, here we see a representation of notable coordinates, how they are stored. This VMAP project also uses an HDF5-based data container because it's vendor neutral. And we stored all the different properties which are of interest. Yeah, history variables and orientations and nodes are different format, which is called VMAP. So if you're interested, it has a big project website, so you can look into it and see the project, the progress of this project as well. Here you see an exchange between LS-DYNA and Abacus data. Provided the VMAP LS-DYNA format, and some other third party transferred it into Abacus, but it works vice versa as well. Finally, we started to work on a license server system for Envyo. So Envyo is an extra tool actually, which is provided by DYNAmore. It does not come with LS-DYNA. It has to be licensed automatically, differently. It's provided by us for the license server, which is basically nothing else than another program which holds the license server executable, some libraries, and the licenses itself. And then we do establish a communication via TCP/IP report. So if you are a user, you also have your Envyo executable, and you have a license. Envyo gets some information of that license regarding which port shall I use for the communication, to which IP address do I have to send these information. It's going to send this information to the server. It's going to check the information which is required and going to give the OK or the decline of the respective sub-user to consider if the program works or not. Tested it internally on our own cluster, which is running on Linux. We haven't tested the license server system on Windows yet. We've also tested it, let's say, externally with our DYNAmore Nordic colleagues. So they got it to work as well. So that would now make it possible for us also to go to, say, larger companies and not to provide just node licenses for Envyo, but also large amount of licenses using this license server system. Future plans in summary. I do have some projects which are resting since a couple of years. One of them is printing, where I started to read G-code paths and make them accessible in a DYNA input file. Yeah, it's kind of, people come up with so many different ideas, so I'm kind of stuck with this, I think, since last year. Seen these simulations from JSOL. I want to work on those since, yeah, 2 years at least, and take these meso models to calculate orientation tensors out of them and make them accessible for MAT 157 or 215. Nevertheless, we might have a project coming up where I actually need to do this. So if the pressure gets higher, that probably might help me to do some progress here. I still think it's an interesting thing, and I'm looking forward to finally working on it at some point. So I'm going to conclude with this last slide, which basically summarizes everything I've said, I think. So Envyo is available for both Windows and Linux operating platforms. So we don't have any restrictions on that. Test versions can be requested at DYNAmore through our website. If you go to DYNAmore products, the Envyo is listed as one of the products, and then there's like a formula which you fill in and send it to us, and then you get a test license. I always say preferably with a small application example. Nevertheless, you've seen that we do have started to create a set of small application examples with which we can hook you up with, so you can get started and see if this is usable for you. The current activities, they still include the equation parser implementation. As I said, this for now just refers to history variables which are introduced through initialization. I will link this to all other history variable handling as well, so that all the history variables which are mapped can then be evaluated on the target mesh. We are thinking about parallelization since quite a while to speed up the mapping process. As you've seen, we started the GUI implementation. We will keep on working on that because it's not applicable to all the features which we have. Another topic is processing of GOM binary result data to make them accessible as well. You've seen that LS-OP, for example, has a feature for that. We want to put something similar into Envyo as well, but for, let's say, different purposes at least. Still mapping of thermal history is something which I want to do, and just for curiosity, but I think this is something I'm going to do soon, is to create temperature curves or to get the temperature curves out of third-party simulation software and use them together with much generalized phase change. Otherwise, feel free to contact us, to use the software, to give us feedback, because software just lives from feedback. As you see, we have small application examples. Some things work on those. Then you have another topic, another bigger example. You have issues in this other example as well, and then well, you get stuck there. And the software is, if you don't tell us, we can't improve it. So please feel free to contact us to try to use the software, report feedback, and we'll try to make it better and better and more accessible and more usable. That's the intention. So this is the end of my talk. If you have questions, I provided my email address here at the bottom. So it's cl or christian.liebold@dynamore.de. Otherwise, I think my colleague Mike will post a questionnaire in the chat where you can give us feedback on this webinar series. I'd be happy to have some of you in the composite course, which has been given from May 18th to May 20th. If you're interested, it's not free of charge though. Otherwise, have a good weekend, and I was happy to have quite a few people in this presentation. Thank you and have a good day.